So good morning everyone. So this is Raghav. So today we will be discussing regarding this degrees of freedom. So how to calculate degrees of freedom of a mechanism. Okay. So degrees of freedom is very important for GATE. Every year you will get 1 mark from degrees of freedom. So from GATE point of view. If you see this degrees of freedom, so what is degrees of freedom? So degrees of freedom is nothing but, so it indicates number of independent related motions possible. So both the translation and rotation between a pair. Or I can define this degrees of freedom like this also. So degrees of freedom is defined as minimum number of independent parameters needed to describe position and motion of the system. So if I take an unconstrained body in space, so unconstrained in the sense no restriction. So this body has no restriction in space. So for this body, if you see, number of independent related motions we call it as degrees of freedom. For this, if you see, so it can move in x direction, so it can move in y direction, and it can move in z direction. So it can rotate about x-axis, it can rotate about y-axis, and it can rotate about z-axis. So if you see this body has 3 translation motions and 3 rotational motions. So total degrees of freedom for this system, so which is unconstrained in space, is 6. So if I take a body in a plane, so if I say this body is supposed to move in a plane, so it cannot leave this plane. So if you say unconstrained body in a plane, so it describes 3 degrees of freedom. If you say it can move in x direction, it can move in y direction, and it can rotate about z-axis. So it has 2 translational degrees of freedom and 1 rotational degrees of freedom. So I am saying that degrees of freedom is nothing but number of independent related motions. So it's nothing but independent related motions you have to count. If you see this, so I can move in x direction, so without moving in y direction. So I can move in y direction without moving in x direction. I can rotate, so without doing any translation on x and y directions. Or I can do like this. I can move this pen simultaneously in x and y directions. So I can rotate and I can move. So I can see if you see these 3 motions are independent. So if I take a nut and screw, so if you see the nut and screw, so the 2 relative motions between nut and screw are not independent. So I cannot rotate without translation, or I cannot translate without rotation. So the 2 degrees of freedom, it has one is rotation and translation, the nut. So if you look at the 2 degrees of freedom, so they are not independent. Sorry, they are not independent, they are dependent. So there if you see for a nut and screw pair, degrees of freedom is only 1. So we need to count number of independent relative motions. So there the number of independent relative motions is only 1. The 2 relative motions are dependent. And if you see here, now we'll develop a mathematical model for calculating degrees of freedom of a given mechanism. Now see here, so if I say the system is like this, so our definition was like this, so this is your system. So if I take the system in a plane, this is my system. So if you look at this t, I can move this t in x direction, I can move this t in y direction, I can rotate this t. So these are 3 independent related motions. I said degrees of freedom for this system is 3. There is one more definition. So degrees of freedom is nothing but minimum number of independent parameters needed to describe a position and motion of the system. So earlier t was here, after some time, let me say t, so t has moved to a new position like this. So I want to describe this motion. So to describe this motion, how many minimum number of independent parameters are needed? So we call that as degrees of freedom. So I can say like this, so t was here, so this point moved here by distance x, so it moved by distance y, and if you see, it has rotated by an angle theta. So I can say degrees of freedom for this system is nothing but 3. So I need a minimum of 3 parameters, independent parameters, to describe this position and motion of the system. Now we will develop a mathematical model for calculating degrees of freedom of a kinematic chain or a mechanism. I think you know the difference between a kinematic chain and a mechanism. So kinematic chain is a closed chain, where the relative motions are constrained. They are not free to move wherever they want. So the relative motion between these elements of the pair is constrained. And if in this kinematic chain, if you fix one link, we call that as a mechanism. We have already seen this. Now if you see here, so if I take a system like this, so this is my system. So what is degrees of freedom for this system? So if you see this system, I can move this t in x direction, I can move the t in y direction, I can rotate t. So I can say there are 3 independent related motions. So I can say degrees of freedom for this system is 3. So if I say the system has 2 elements like this, number of elements are 2 in the system. So this is my system. So if you look at the system, I can move this t in x direction, I can move t in y direction, I can rotate t. So these are 3 degrees of freedom. Now if you look at x, so without affecting the motion of t, I can move x in y direction, x in x direction, I can rotate this x. So I can say this t describes 3 degrees of freedom and this x describes 3 degrees of freedom. So after some time, if this t goes to new position, to describe that motion I need 3 parameters. So if x goes to some new position, to describe position and motion of x, I need 3 more parameters. So I can say degrees of freedom for this system is 6. So if I say my system has 3 elements like this. So this is one element, this is second element, and this is third element. So the system has 3 elements. So if you look at this, I can move this t in x direction, y direction, I can rotate this t. And if you look at this x, so I can move this x in x direction, y direction, I can rotate this x about z axis. The same thing I can do with a also. So to describe this motion, I need 3 parameters. To describe this motion, I need 3 parameters. To describe this motion, I need 3 more parameters. So here if you see degrees of freedom for this system, it is 9. So when I had one element, degrees of freedom was 3. When I had 2 elements, degrees of freedom was 6. So when I had 3 elements, degrees of freedom was 9. So if my system has n number of elements, so I can say degrees of freedom, so it would be 3n. If there are n number of elements in the system, so degrees of freedom of this system will be 3n. And if you see, if you look at a mechanism, the mechanism one link is fixed. Now let's see what happens if I fix one link. So if I fix this t, so I cannot move this t in x direction, I cannot move this t in y direction, I cannot rotate this t. So when I fix this one, so earlier it was having 3 degrees of freedom, it lost 3 degrees of freedom. So here also the same thing, if I fix this t, so I cannot move this t. So I don't need any parameters to describe this motion, but I can move this in x in 3 directions. So I can say like this system has only 3 degrees of freedom. This t has lost 3 degrees of freedom. So degrees of freedom now is nothing but 3. So here also if I fix this t, so I lose 3 degrees of freedom. So in a mechanism you will be fixing one link, so that link cannot move in x direction, y direction, cannot rotate. So for that link all the 3 degrees of freedom is lost. So if there are n number of links in the mechanism, in a kinematic chain, degrees of freedom will be 3n. So if one link of your system is fixed, so then degrees of freedom will be 3 into n minus 3. So I can write 3 into n minus 3 like this, 3 into n minus 1. So I can say like this. So if you see the first one, in a kinematic chain no link is fixed. So if there are n links in a kinematic chain, degrees of freedom will be 3n. But in a mechanism one link is fixed, degrees of freedom will be 3 into n minus 1. Now let us see what happens if I establish a connection between these links. So in a mechanism all the links are connected. In a kinematic chain all the links are connected. Now see here what happens if I establish a connection. Now see here. So if you look at this system, this is t, this is x. So for this system if you see, so degrees of freedom, I can move this t in x direction, y direction, I can rotate this t. So to describe position and motion of x, I need 3 more parameters. Therefore I can say degrees of freedom for this system is 6. Now let us establish a connection with the help of a lower pair. So lower pair is nothing but a turning pair or sliding pair. So where the elements of the pair has a surface contact. That is lower pair. So if you look at turning pair is a lower pair. I connected x and t with the help of a turning pair. Now see here, now see this system. So I established a connection with the help of a lower pair. Now see here, so if I hold t, I can rotate x about this turning pair. I can rotate x about this turning pair. This is 1 degree of freedom. Now see here, x is rotating. I can move t in x direction. I can move t in y direction, and I can rotate t also. X is rotating with some speed, omega 1. T is moving with some speed in x direction, with some speed in y direction, and t is also rotating. So x is rotating, t is rotating, t is moving in x direction, t is moving in y direction. I can say this system has degrees of freedom 4. Now see here, so if the system has 3 elements like this. So to describe position and motion of this system, I need 3 parameters. To describe position and motion of this system, I need 3 parameters. For this one, I need 3 parameters. I can say degrees of freedom of this one is 9. So if I establish a connection with the help of a lower pair, now see here, I connected A to x with the help of a turning pair, and I connected x to t with the help of a turning pair. So I am holding t and I am holding x. So I can rotate A about this hinge. So A is rotating with omega 1 speed, that's 1 degree of freedom. Now I am freeing x, so x also can rotate about this hinge, so that is 2 degrees of freedom. Now I can move t in x direction, I can move t in y direction, I can rotate t also about this hinge. So t has 3 degrees of freedom, x is rotating and A is also rotating. So this system has 5 degrees of freedom. Now see here, So when there was no connection, the system has 6 degrees of freedom for 2 elements, and when I established a connection, degrees of freedom is 4. So here there is no connection, degrees of freedom was 9. When I established a connection, degrees of freedom reduced to 5. So whenever you establish a connection, so they are not free to move wherever they want. So now they are restricted. The motion is constrained now. Now if you see, so when there was one lower pair, so it was 6. When I established a connection with one lower pair, so I lost 2 degrees of freedom. Here if you see, when there is no lower pair, I can say when there is no connection, degrees of freedom was 9. When I established a connection with the help of 2 lower pairs, so degrees of freedom reduced to 5. So I can say, so I lost 4 degrees of freedom. So for one lower pair, I lost 2 degrees of freedom. For 2 lower pairs, I lost 4 degrees of freedom. If there were 3 lower pairs, so I would have lost 6 degrees of freedom. I can say like this, for each lower pair, I am losing 2 degrees of freedom. If there are L number of lower pairs inside your system, so you will lose 2L number of degrees of freedom. For each lower pair, we will be losing 2 degrees of freedom. So here if you see, in a kinematic chain, if there are N number of links, so degrees of freedom will be 3 into N, and if these N links were connected with the help of L number of lower pairs, for each lower pair, degrees of freedom will come down by 2L. For each lower pair, degrees of freedom will reduce by 2. So here in a mechanism, if there are N links, number of movable links will only 3 N minus 1, degrees of freedom will be 3 into N minus 1. If these N minus 1 links are connected with the help of L number of lower pairs, degrees of freedom reduces by 2L. Now let us see what happens if I establish a connection, so with the help of a higher pair. Now see here. So I have 2 elements like this. So I can move this disk in x direction, y direction, I can rotate this disk, so 3 parameters. So I can move this one in x direction, y direction, I can rotate this one, so 3 more parameters. I can see degrees of freedom for this system is 6. So if I establish a connection between these 2 elements, so if I say these 2 elements are forming a kinematic pair, so on the kinematic pair is a higher pair here. Now you can see, so I can rotate this disk. I can rotate this disk, so there is 1 degrees of freedom. I can translate this disk, so 1 more degrees of freedom, 2 degrees of freedom. This disk can be rolled and this disk can be translated, 2 degrees of freedom. And if you look at this one, so I can move this in x direction, I can move this in y direction, and I can rotate this. So disk is describing 2 degrees of freedom and this has 3 degrees of freedom. So total if you see, 5 degrees of freedom. This system has 5 degrees of freedom. Earlier when there was no connection, so the system has 6 degrees of freedom. Now I established a connection with the help of a higher pair, I lost 1 degree of freedom. Whenever there is a higher pair inside your system, so degrees of freedom reduces by 1. For each higher pair, so I will be losing 1 degree of freedom. So if there are h number of lower pairs in the system, so degrees of freedom reduces by h. Now see here in a kinematic chain, if there are n number of links, degrees of freedom will be 3 into n. So if there are L number of lower pairs, for each lower pair I will be losing 2 degrees of freedom. And if there are h number of higher pairs, so I lose h number of degrees of freedom. And the same thing with the mechanism. So now finally we got an equation for calculating degrees of freedom of a kinematic chain and degrees of freedom of a mechanism. And for a kinematic chain it is like this. Kinematic chain, so degrees of freedom is 3 into n. If there are n links inside the system, degrees of freedom will be 3 into n. So if there are L number of lower pairs, for each lower pair, degrees of freedom reduces by 2. If there are L number of lower pairs, degrees of freedom comes down by 2L. And for each higher pair, I lose 1 degree of freedom. If there are h number of higher pair, degrees of freedom reduces by h. Now see here, degrees of kinematic chain for a kinematic mechanism. For mechanism, degrees of freedom. So if there are n links in a mechanism, so 1 link will be fixed. Therefore, I can say degrees of freedom will be, so I have only n minus 1 moving links, degrees of freedom will be 3 into n minus 1. And if there are lower pairs, for each lower pair, degrees of freedom reduces by 2. If there are n number of lower pairs, degrees of freedom reduces by 2L. And for each higher pair, I will lose 1 degree of freedom. If there are h number of higher pair, degrees of freedom reduces by h. So this is degrees of freedom for kinematic chain, and this is degrees of freedom for a mechanism. So mechanism and kinematic chain, the difference is 1 link is fixed in a mechanism. And this equation, if you see, this is also called as Kutzbach's criterion. This is called as Kutzbach's criterion. So Kutzbach's criterion is a generalized equation. So the mechanism having higher pairs or lower pairs, so So I can use this equation for calculating degrees of freedom. There's one more criterion, that's groupless criterion. So that's applicable only for those mechanisms which contain single degree freedom joints. I can say which contains only lower pairs. So this is the equation for degrees of freedom. Now let us solve a few problems. So calculate degrees of freedom for this system. So if you see, so this is link number 1 fixed link. So this is link number 2, this is link number 3, this is link number 4. So I can say number of links are 4. And if you say number of lower pairs, so link 1 and link 2 are connected by turning pair 1 lower pair, second turning pair, second lower pair, third lower pair, fourth lower pair. So number of lower pairs are 4. So if you look at the mechanism, there is no higher pair. And degrees of freedom, if you see, it is 3 into so n minus 1 is the mechanism, so minus 2 times lower minus higher. I can say 3 into n minus 1 minus 2 times lower. Degrees of freedom for this mechanism is 1. So what does degrees of freedom 1 indicates? So degrees of freedom 1 indicates that for a unique input, you will be having a unique output. So here if I give one input, so I will be getting a predictable output. Now we'll solve one more problem. So calculate degrees of freedom for this system. So this was asked in GATE. And if you say this one, so this is link number 1, so this is link number 2, this is link number 3, this is link number 4, this is link number 5. Number of links here are 5. Number of links here are 5. Number of lower pairs, if you see, 1 turning pair, second turning pair, third turning pair, fourth, fifth. Number of turning pairs are 5. So if you look at the mechanism, there are no higher pairs. And if I calculate degrees of freedom for this system, it is 3 into n minus 1, so minus 2 times lower minus higher. So degrees of freedom for this system, if you see, it's 2. Degrees of freedom is 2. So what does degrees of freedom 2 indicate? So see here, if you look at this particular mechanism, so if I give one input for this link number 2, so if I give some input for link number 2, so I cannot predict the output here. The predict here is not, the output here is not constrained, it's not fixed. Now see here, there are two possibilities. So one, when I rotate this link number 2, so link number 4 and move in some fashion so that link number 5 also rotates clockwise. Or sometimes, so it may happen like this, when you rotate link number 2, so link number 2 displaces, link number 3 comes like this, link number 4 will stay like this, and there won't be any effect for link number 5. So this may happen. I can say there are two possibilities. So one is link number 5 is also rotating, and second one is link number 5 is not moving at all. So I can say like this, so degrees of freedom 2 or degrees of freedom of a mechanism indicates number of inputs needed so to make the mechanism constrained. Now see here, so here degrees of freedom is 2, so if I give 2 inputs, you can give inputs wherever you want, but if you need to give 2 inputs. So if I give 2 inputs for this mechanism, then I can predict the output. So here degrees of freedom is 1, so 1 input is needed to predict the output. So here I need to give 2 inputs to make the mechanism constrained. So constrained in the sense, it's completely constrained, only one output, unique output. So I need to give 2 inputs here to get a unique output. So the inputs can be given wherever you want. So degrees of freedom of a kinematic pair indicates number of independent relative motions possible, and degrees of freedom of a mechanism indicates the same thing, but I can define like this also. So that is number of number of inputs needed to make the mechanism constrained. This is one more definition. So here I need to give, there are 2 independent relative motions possible, but to have only one, I need to give 2 inputs for this mechanism. So whenever a mechanism is given to you and they are asking you to calculate degrees of freedom, so first identify number of links inside the mechanism, number of lower pairs in the mechanism, and number of higher pairs in the mechanism. Substitute in the formula. Now calculate degrees of freedom for this system. calculate degrees of freedom for this system. So if you look at this system, so it's a fixed link, link number 1, link number 2, link number 3. So number of links are 3, number of lower pairs if you see, it's 1 lower pair, second lower pair and third lower pair. Number of lower pairs are 3. And if you look at higher pairs in the mechanism, there are no higher pairs in the mechanism. And if I calculate degrees of freedom for this system, it's a mechanism, it's 3 into n minus 1 and it's 2 times lower, no higher. And if I find degrees of freedom, it's 0. So when I get degrees of freedom 0, there is no relative motion possible. And if you look at a mechanism, so main aim of a mechanism is to transfer the motion and transform the motion. So mechanism is used for transforming the motion. So you may be having some kind of motion, you may be having rotary motion, I want a reciprocating motion like your, if I take a compressor, reciprocating compressor. Input is, so rotary motion, so I run compressor with the help of a motor, but the output needed, I need to reciprocate the piston. So here I am transforming a rotary motion into reciprocating motion. Or if I take an IC engine, so reciprocating motion of the piston is transformed into rotary motion of crankshaft. So here I need transformation of motion, and for transformation of motion, so we use a mechanism. So mechanism is mainly used for transforming the motion. But here if you say there is no relative motion possible, therefore I can say I cannot transform any motion with the help of this mechanism. So these kind of mechanisms where you cannot transform the motion, but you can transfer the forces. So these are called as structures. So whenever degrees of freedom of a mechanism is 0, it is called as a structure. It is used for transferring the forces. So here also the same thing. So whenever you find a hatched region like this, it's a hatched part. So hatched part indicates it's only single link. So this hatched part, it's a single link. So single link, link 1, link 2, link 3, link 4, and it's a hatched part, it's a single link, link 5. So here if you see, number of links are 5. So number of lower pairs, it's 1, 2, 3, 4, 5, 6. Number of lower pairs are 6. Number of higher pairs in the mechanism are 0. If I calculate degrees of freedom, it's 3 into n minus 1, so minus 2 times lower, I can say degrees of freedom is 0. So here this is also a structure. So structure I cannot transform the motion, but I can transfer the forces. So if I calculate degrees of freedom this system, this is like this. So whenever you find a continuous line like this, it indicates it's a single link. So I can say like this, it's a link number 1, single link, it's link number 2, single link, it's link number 3, and link number 4. Whenever you find a continuous line, it's a single link. So if these two are different links, I would have indicated like this. So this is one link, this is second link. But here it's a continuous line, therefore it's a single link. So if you calculate degrees of freedom for this system, so number of links are 4. So number of lower pair, it's 1 lower pair, second lower pair, third lower pair, fourth lower pair, fifth lower pair. Number of lower pairs are 5. So number of higher pairs in the mechanism are 0. So if I calculate degrees of freedom, it is 3 into so n minus 1, so minus 2 times lower. So degrees of freedom is minus 1. So degrees of freedom negative indicates that, so it's a superstructure. Degrees of freedom is 0. There are no relative motions possible. So degrees of freedom is negative. So though you remove some links from this mechanism, so there won't be any relative motions further. So this kind of mechanisms where degrees of freedom is negative, so we call them as superstructures. There is no difference between a structure and a superstructure. The only difference is that, so structure and superstructure both are used for transferring the forces, but superstructure can withstand for large amount of forces. I can say it can resist for large amount of loads. And if you look at these railway bridges, foot-over bridges, and your towers, electrical poles, so most of these are superstructures. So they can take more load, they can carry more load. They cannot transform the motion. There won't be any relative motion between elements of the track or elements of the, what do we say, that foot-over bridge. They can only transfer the forces to ground. Now calculate degrees of freedom for this system. Calculate degrees of freedom for this system. So if you look at the system, so it's a fixed link, link number 1. This is also fixed part, link number 1. This is also fixed part, link number 1. This is also fixed part, link number 1. So this is link number 2, this is link number 3, this is your slider link number 4, so this is link number 5, so this is link number 6, it's hatched part, I told you single link number 7 and link number 8. Number of links here are 8. Number of links are 8. And if you look at number of lower pairs here, so it's one turning pair, it's lower pair, turning pair, it's a lower pair, so it's a turning pair, lower pair, so 1, 2, 3, 4, 5, 6, 7 lower pairs are there, 7 turning pairs. And if you look at this point, it's a sliding pair. Link number 1 and link number 4, it's a sliding pair. It's also lower pair plus 1. And if you look at here, this point, at this point, if you look at this hinge, if you see, so link number 4, link number 3, link number 5, 3 links are connected. If 3 links are connected at a single point, so we call it as a ternary joint. So ternary joint. So these kind of joints are called as binary joints. 2 links are connected at a point. It's called as a binary joint. So link number 1 and link number 2. So I can say one binary joint is equals to one lower pair. So if 3 links are connected at a point, so link number 1, link number 2, link number 3, so it's called as ternary joint. So one ternary joint is equivalent to 2 lower pairs. So if 3 links are connected, I can say, so one ternary joint is equivalent to 2 binary joints. And one binary joint is one lower pair, 2 binary joints, 2 lower pairs. So if 4 links are connected at a point, it is called as quaternary joint, and one quaternary joint is equals to 3 binary joints. I can say it's equal to 3 lower pairs. So I can say like this. So if you know the position of link 1, to know position of link 2, I need only one parameter. So therefore I can say it's 1 degree of freedom, one lower pair. So here if you see, so if I take link number 1, so from link number 1, so if I know this angle, so position of link number 3, and if I know this angle, so it's more than enough. So therefore I can say, so one ternary joint is equivalent to 2 lower pairs. So here I can say one binary joint is one lower pair. So here 2 binary joints is equivalent to 2 lower pairs. I can say number of independent parameters needed here are only 2. So I don't need this angle. So I don't need to know the angle between 2 and 3. So number of degrees of freedom, so here are only 2. Now see here, so for this case if you see, so with respect to link number 1, so 1 and 2 is one lower pair, 1 and 3 is one lower pair, 1 and 4 is one lower pair. Therefore I can say there are 3 lower pairs. So here number of independent parameters needed, from 1 and 2 one angle, 1 and 3 is one angle, 1 and 4 is one angle. So I don't need to know the angle between 2 and 3 and 3 and 4. So here if I know these 3 angles, so I can look at the position of any other link with respect to any other link. So therefore I can say one binary joint is equals to one lower pair, so one ternary joint is equivalent to 2 lower pairs, so one quaternary joint is equivalent to 3 lower pairs. So and here if you see, at this point if you see, so link number 3, link number 5, link number 4, 3 links are connected. 3 links are connected is nothing but it's a ternary joint, and one ternary joint is equivalent to 2 lower pairs. So already I had 7 plus 1, 8, 8 plus 2, 10. Number of lower pairs here are 10. And if you look at higher pairs in the mechanism, number of higher pairs here are 0. There are no higher pairs. And it's a mechanism, so degrees of freedom, if you see, it's 3 into n minus 1 minus 2 times lower minus higher. Degrees of freedom, I can say it's 1. So for this mechanism, degrees of freedom is 1. So whenever a mechanism is given to you, first identify, so how many binary joints are there inside the mechanism, and how many ternary joints are there inside the mechanism, and how many quaternary joints are there inside the mechanism. It's very, very important. So as soon as the mechanism is given for calculating degrees of freedom, first look at the mechanism. So look, are there any binary joints? How many binary joints are there? How many ternary joints are there? How many quaternary joints are there? So first step you need to do. And in 2012 there was one question in GATE. And the question is like this. So calculate the degrees of freedom for this mechanism. Calculate degrees of freedom for this mechanism. So length of all the 3 links is same. So calculate degrees of freedom for this mechanism. And if you look at this mechanism, so number of links in this mechanism are like this. It's a fixed link, link number 1, link number 1. It's link number 2, so it's link number 3. It's link number 4. It's a continuous line, I can say it's link number 5. So number of links inside this mechanism are 5, and number of lower pairs, if you see, it's 1 lower pair, 2nd lower pair, 3rd lower pair, 4th, 5th, 6th. Number of lower pairs here are 6, and if you see here, number of higher pairs is 0. So if I calculate degrees of freedom for this mechanism, it's 3 into, so n minus 1, so minus 2 times lower pairs, number of lower pairs are 6, so minus 2 times 6. if you see degrees of freedom for this mechanism, it comes out to be 0. But if you look at the mechanism, configuration of the mechanism, you can imagine this. So when I rotate link number 2 like this, link number 3 rotates and link number 4 also rotates. Degrees of freedom 0, it indicates that there is no relative motion between elements of the mechanism. But here, so I have relative motion between elements of the mechanism. So what's happening here? See here, if you look at Kutzbach's criterion was like this. So Kutzbach's criterion is 3 into n minus 1, so minus 2 times lower minus higher. This is Kutzbach's criterion. So if you look at this Kutzbach's criterion, so for calculating degrees of freedom of planar mechanisms, so here in this equation, he considered number of links, number of lower pairs and number of higher pairs. He never looked into the geometry of these links. He did not consider so geometry of the links and length of links and other parameters for calculating degrees of freedom. He just took into account number of links, number of lower pairs and number of higher pairs. So due to this reason, so since he did not consider the geometry of links and other dimensional parameters of the links, so this equation, so Kutzbach's criterion, will fail in few cases. So this will give some incorrect results in few cases. And this is one such case. So there are two cases. So one is case 1. So I will be discussing this as cases. So this is one case 1. So there are two cases, there are two different situations where this Kutzbach's criterion is going to fail. So this is one situation where Kutzbach's criterion is going to fail. See here, if you look at this mechanism, so for this mechanism, if you see, so in a mechanism, if you take number of links in a mechanism, every link should introduce some restrictions inside the mechanism. So if the link is not introducing any restrictions, I can say there is no use of that link. So I can remove that particular link. So here if you see, so if I take a 4-bar mechanism like this, if I take a 4-bar mechanism, every link is introducing some restrictions. So or I can say like this, so here this link has its own importance, this link has its own importance. So if I remove this particular link, functioning of the mechanism is changing. So, or I can say if I remove this link, functioning of the mechanism is going to change. So every link is introducing some restrictions, some constrained motions. But here if you look at the mechanism, this particular mechanism, so in this mechanism number of links are 5. But if you see the functioning of the mechanism is when I rotate link number 2, link number 3 is rotating, link number 4 is also rotating. But if I remove one of these links, if I remove link number 2, so if I remove link number 2, now see here, what's happening? So link number 3 is rotating, link number 4 is also rotating. Or, so keep link number 2 like this, so now remove link number 3. Or keep link number 3 like this, now remove link number 4. So what I'm going to say is, so though you remove link number 2 or link number 3 or link number 4, if you remove one of these 3 links, the functioning of the mechanism is not changing. The functioning of the mechanism is not affected. I can say like this, sometimes your mechanism may be having one or more links which do not introduce any extra restrictions inside the mechanism. So such links are known as redundant links. And these redundant links must not be counted for calculating degrees of freedom. Here if you see, so if I remove link number 3, the functioning of the mechanism is not changing. So it indicates that, so link number 3 is not introducing any extra restrictions. So I can say, so link number 3 is here, but if you remove link number 4, keep link number 3 and remove link number 4. Now also the functioning of the mechanism start changing. Therefore I can say, so link number 4 is not introducing any extra restrictions. So here I can say like this, one of the links, either 2 or 3 or 4, can be considered as a redundant link. Now see here, if I remove link number 3 and if I remove link number 4, functioning is going to change. But if I remove only one link of these 3 links, functioning of the mechanism is not changing. Therefore I can say, so here among 2, 3 and 4, one link is a redundant link. It is not introducing any extra restrictions inside the mechanism or extra constraints inside the mechanism. So such kind of links which do not introduce any extra restrictions inside the system are called as redundant links. Here one of the links, so 2, 3, 4 can be considered as a redundant link. So if I assume there is one redundant link in these 3 links, 2, 3, 4, then effective number of links, I can say though I eliminate this redundant link, effective number of links in this mechanism are only 4 with 4 turning pairs, I can say 4 lower pairs. Repeating again, sometimes a mechanism may have one or more links which do not introduce any extra restrictions inside the mechanism. Such links are known as redundant links and should not be counted for calculating degrees of freedom. So I need to eliminate that particular redundant link. So I eliminated that redundant link. So after eliminating the redundant link, now calculate, so how many effective number of links are there inside the mechanism, and how many effective lower pairs are there, and how many effective higher pairs are there after eliminating that redundant link. Now here if you see, so effective number of links are 4 with 4 lower pairs, and if you look at higher pairs, there are no higher pairs. So if you calculate degrees of freedom for this system, it's 3 into n minus 1, so minus 2 times lower. I can say degrees of freedom for this system is 1. Yes, degrees of freedom is 1. This is one case where Kurzweil's criterion fails. There's one more case where Kurzweil's criterion fails. I'm discussing that as case 2. It's a slider, it's a sliding pair. Okay, it's a slider. So here if you look at this mechanism, so it's a link number 1, fixed link, it's a link number 2, it's a link number 3, it's a link number 4. Okay, number of links are 4, and if you calculate number of lower pairs, it's one lower pair, turning pair, second lower pair, it's a sliding pair and it's a sliding pair. There are 2 sliding pairs and 2 turning pairs, therefore I can say number of lower pairs are 4. And if you look at the mechanism, number of higher pairs, no higher pairs are there in the mechanism, I can say number of higher pairs are 0. So if I calculate degrees of freedom for this mechanism, so I will get degrees of freedom as 1. But here if you look at the mechanism, so when I try to rotate link number 2 like this, when I try to rotate link number 2 like this, when I try to rotate link number 2, if you look at link number 3 will get jammed, so inside the sliders, link number 3 will get jammed inside these 2 sliders, slots. And there won't be any relative motion. But here I got degrees of freedom is 1, but here there is no degrees of freedom possible. But here the result got is inaccurate. I can say Kurzweil's criterion failed in this case. So why Kurzweil's criterion failed in this case? Because, so it's case 2, sometimes what happens is, inside your mechanism, there may be some links. There may be some links inside your mechanism. There may be one or more links inside your mechanism, so which can be moved, so without imparting motion to other elements of the machine or mechanism. So here if I say, if I take a 4-bar mechanism, so if I take a 4-bar mechanism like this, so this is 4-bar mechanism. So I cannot move any links of this 4-bar mechanism. So if I try to move any one of these links of 4-bar mechanism, so all of the links gets moved, gets displaced. So sometimes in your mechanism, so it may have one or more links which can be moved without imparting any motion to other elements of the mechanism. So here in this mechanism if you see, so I can move link number 3 without imparting any motion to link number 2 or link number 4. So I can reciprocate link number 3 like this. So I can reciprocate link number 3 like this, so without imparting any motion to link number 2 or link number 4. So such links are said to have redundant degree of freedom. So whatever the degrees of freedom you are getting here, that is that redundant degree of freedom. So here, so one link is there, so I can move this link, so without giving any motion to link 2 or link 4. Such links are known as a redundant degree of freedom. So this link is having a redundant degree of freedom, and that what you are getting is a redundant degree of freedom. There are 2 cases. So case 1 is a redundant link. So redundant link is the one which do not introduce any extra constraints inside the mechanism. So you can eliminate that link, then calculate the effective number of links, effective number of lower pairs, effective number of higher pairs. And a redundant degree of freedom. So it's nothing but, so some of the links you can move inside the mechanism without giving any motion to other links of the mechanism, So such links are said to have redundant degree of freedom. So here link 3 is having redundant degree of freedom. So calculate number of links having redundant degree of freedom. So if your mechanism is having any links with redundant degree of freedom, so degrees of freedom is calculated like this. So 3 into n minus 1, so minus 2 times lower, minus higher. This is your Kurzweil's criterion, minus number of redundant degree of freedom. So here, if you look at this case, so number of links are 4, number of lower pairs are 4, number of higher pairs is 0, and number of links having a redundant degree of freedom. Redundant degree of freedom in the sense, how many number of links you can move without giving any motion to other links of the mechanism. Here only one link I can move, I can say only one link is having a redundant degree of freedom. So now if you calculate degrees of freedom, it's 3 into n minus 1, so minus 2 times lower, so minus higher, so minus number of links having redundant degree of freedom. If I calculate degrees of freedom, it's 0. So there are two cases where Kurzweil's criterion fails. One is a case of redundant link, and second one is a case of redundant degree of freedom. So whenever a mechanism is given and asking you to calculate degrees of freedom, keep these 3 points in mind. First point is that, so when a mechanism is given to identify how many binary links, ternary links, quaternary joints, binary joints, ternary joints, quaternary joints are there inside the mechanism. And second point is that, so whenever a mechanism is given, so first check how many redundant links are there inside the mechanism, or you check for how many links are having redundant degrees of freedom. These 3 points must be kept in mind. So identifying ternary, quaternary joints, so identifying redundant links, identifying links with redundant degree of freedom, these 3 cases. So once there was a question based on this redundant link in the previous question, and there's no question based on this redundant degree of freedom. You may get question from redundant degree of freedom. Until now there was no question, so from this ternary joints and quaternary joints also, every time there was a question only from this binary joints. So there are chances to get question from these ternary joints and quaternary joints also. So we'll see one more question. So calculate degrees of freedom for this mechanism. It's a roller. The roller is hinged at this point, hinged at the center, I can say. So this is your cam. Cam with the roller follower, roller faced follower. So if you look at this mechanism, so it's a fixed link number 1, it's a fixed link number 1. Cam is link number 2, this roller is link number 3, and the follower is link number 4. So if you see number of links are 4, so number of lower pairs, so it's 1 turning pair, second turning pair, 1 sliding pair. So number of lower pairs are 3, 2 turning pairs and 1 sliding pair. And number of higher pairs, if you see, so 2 and 3 are connected by a point contact. Number of higher pair is 1. So if you calculate degrees of freedom, it's 3 into n minus 1, so minus 2 times lower minus higher. I guess it's 9, so minus 7, I can say degrees of freedom is 2. So for this cam follower mechanism, degrees of freedom is 2, but for a cam follower mechanism, degrees of freedom is 1. So I can rotate the cam to reciprocate the follower. So only one relative motion is possible. So for one input, I have only one output. So input is rotating the cam, so follower is reciprocating, that is the output. But here I got degrees of freedom as 2. So here also Kurzweil's criterion failed. Why Kurzweil's criterion failed? Because, so if you look at this particular roller, that's link number 3, the roller is hinged at the center. When I rotate the roller, so link number 4 will not move and the link number 2 will not move. So I can say there is some link inside my mechanism which I can move without imparting motion to other links of the mechanism. So such links are said to have redundant degree of freedom. Here link 3 is having redundant degree of freedom. Link 3 is having redundant degree of freedom. So number of links having redundant degree of freedom here is 1. That's link 3. And if you calculate degrees of freedom now, it's 3 into n minus 1. So minus 2 times lower minus higher minus number of links with redundant degree of freedom. So here if you see degrees of freedom, it's 1. So whenever you are calculating degrees of freedom, so first check for types of joints, next check for redundant links, and next checks for link with redundant degree of freedom. So keep these 3 points in mind. Thank you.